So here's I'm going to show you the derivation. It looks messy, but it's not. This is the probability distribution of the states of the system. That includes the parameters. There's no difference between the states and the parameters. States satisfy a differential equation, dx dt equals some function that represents the physics. The parameters have a differential equation. The parameter dt equals 0. Treat them all the same. This is the probability distribution of the states at time n plus 1, jointly with all the measurements up to time n plus 1. And if you write out the arithmetic here, which I urge you not to try to copy down, but will be posted with everything else, you find it divides into two parts. It divides into a part that tells you the probability distribution of the state at time n plus 1, given aspects of the state up until that time. If underlying your model is an underlying differential equation or a statement of discrete time dynamics, this thing depends, the probability distribution of the state at time n plus 1 depends only on the previous state. That's what you mean by a differential equation. This quantity needs interpretation, but this tells you how to modify your probability distribution when you make a measurement. This is called a Markov property, and this is often called a Bayes property. Those are quite general. This has nothing special to do with how you build your model and your system. The quantity that occurs in blue, which is associated with the modification of your probability distribution when you make a measurement, was discussed by Claude Shannon in the 1940s as the conditional mutual information between, in this case, the measurements and the states of the system. We translate that into common day language when we talk about a communications channel, such as the one I showed between the transmitter and the receiver, by translating it into bits that you buy from the internet service provider per second to get information from the net through their circuits into your screen. That tells you that the modification of the probability distribution is associated with the transfer of information in a quantitative way. It's not just words. Once you know the probability distribution and that recursion, you can start at time 0, and you can say, move the system from 0 to 1, make a measurement, and modify the distribution. Move the system from 1 to 2, make a measurement, and modify the distribution. And you can go through the whole selected set of operations during your measurement window, and this is your probability distribution. This is related to the errors you make in measurements, and this is related to the errors that you make in models. If you had absolutely no error in your model, you were spectacularly great, this would be a delta function in the appropriate space saying, if you tell me where you are now, I will tell you exactly where you will be in one step. But as Sebastian showed you, it is much more sensible to recognize that models have errors and to make a choice that parameterizes the way those errors enter this piece of this probability distribution.
So the P in the left side is P that relates...
Which left side?
Left side of the third line. Yeah. No, third line. From above.
That's 1, 2, 3. This one. OK. Sorry. I thought I started here.
It's the P at final time?
It's the P. Capital X is the probability distribution of X at T0, jointly with X at T1, jointly with X at T2, all the way to the final time. And this is the distribution, because these measurements all have errors, at the times, tau 1. Oh. This should read tau 2. Sorry. I wrote this thing on a PC and I put it onto a Mac, and it does whatever it wants. Okay, this is called a 2. And this is the distribution of the measurements with their errors. And this is the joint distribution divided by the P of y to make it conditional. And I write that as e to the minus something. It's often called minus the log likelihood. In physics, we call it the action. All right. Suppose I actually were able to calculate that probability distribution for you. What would you do with it? I mean, you would be awed, of course. But what you would do with the probability distribution is you'd calculate moments of the probability distribution of quantities were of some interest to you. So suppose I have a function on what I call the path, which is the state as it moves along in time. And I would like to know the expected value of that quantity. Well, I have to do this integral. It's the integral over all paths, the probability of the path, times the function, normalized. Not every one of you who took a course in a laboratory course in linear electric circuits went on to take a course in statistical physics, but any of you who did will recognize this formula, and if I'd put a KT underneath the A, you would have recognized it as calculating the partition function, or the moments of a partition function. KT is 1. The fluctuations here are not from thermal fluctuations. They're from errors in the model and errors in the measurement. And this is normalized. So your job is to do this integral. Here's an interesting question, interesting quantity. Suppose I take the quantity you're interested in to be x itself. You'd like to know the expected value of the path of your system starting from some time 0, getting to some final time. And you put here x, and you do the integral. You want to know the moment, the covariance around that mean expected path. You put in here x minus x expected, and you calculate that first moment. You want to know the covariance matrix about it. You know what to do. This is an absolutely critical thing because this physics question guides you to what you want to do with all of this machinery. And I'm going to elaborate on that now. Are there any questions about your job? Here's the action. The action divides into 3 parts. The information transfer. This is Mr. Shannon's conditional mutual information. This is the dynamics in a stochastic setting. And this is the uncertainty that you have when you start out. As I said, this is called the prior. I forgot what's the unprior, posterior? All right, okay, prior, the unprior, and you have to do that integral. So everything about that integral depends upon the structure of this action in this space of paths. All right? Suppose the action had a single beautiful minimum in this space of paths. By the way, the space of paths that we were dealing with in the case of the transistor, because we had 1,000 time steps, each of 10 microseconds making up a 10 millisecond observation time, and we had 3 variables and a control variable and 4 parameters, the space was 4,004 dimensional. So at the simplest possible thing, you have to do a 4,004 dimensional integral, which is no big deal. All right, if A has a minimum somewhere, that means that the probability, e to the minus A, is big. If the probability is big, it's not stupid, in fact, it's smart, to estimate the integral in the neighborhood of where the probability is very big. And if you thought of that all by yourself, congratulations. The person who introduced it into the discussion of doing these integrals is Laplace in 1774. And what Laplace said is, look for the minima of that quantity A. Those are equivalent to the maxima of the probability distribution. Look in the neighborhood of that and approximate the integral by summing up the contributions of all of the maxima of the probability or all of the minima of the action. So in order to find the minima of this function of a very large dimensional quantity, you have to find its extremum point, and the condition is that the second derivative in the neighborhood of that extremum be every direction you go in, you go up, so it really defines a minimum. There are fancy ways to say that. And again, I'm not going to discuss this in any length, but Sebastian said another way of doing that integral is using Monte Carlo techniques, which is basically a method of systematically starting somewhere, hopefully with a smart way of moving through the path space to find the maximum and then estimate the integral there. All right, that's our job. So I'm going to write down what the action looks like in what I call the standard model. There are other people in the world, many of whom work at CERN, who think they have the standard model, but why shouldn't we have one too? And I'll show you the standard model for data assimilation. It makes two further assumptions. The first further assumption is that the errors in your measurements are Gaussian. That isn't always true, but reasonable place to start, because what we get out of this is the standard model is hard enough, and if we change that assumption to a different kind of distribution, maybe it's a Poisson distribution. Greg Hakim assured me that if I was interested in precipitation, it was not a Gaussian distribution because I couldn't have negative precipitation. I think he's right. And the second assumption I'm going to make is exactly the one that Sebastian made, which is that the errors in the model, which can be very complicated, can be represented by Gaussian fluctuations around the model itself. Now, if you think about that for a little bit, that's absolutely wrong. Suppose you made a model of the atmosphere and you forgot something, say viscosity in the atmosphere. You just left the term out of the fluid dynamics equations. Well, that's a model error, but it's not representable by a Gaussian distribution of errors. So that's why I call it the standard model. It gives you a modest model that has some reasonable semblance of reality. And that's the integral we're going to have to do. That turns out to be hard enough, and let me proceed on to that. So here's the standard model. I call the action, I've left off the dependence on the measurements because they're in my library. I'm not going to vary them. This is the variation of all of the states of the model during my measurement window and all the parameters, which I'm treating as states. That's the right way to do it. The state variables that are measured, that is to say the y's, I have capital L of them, and L is much, much smaller than the dimension of the model itself. And I say that x minus y is distributed as a Gaussian. I put the covariance matrix, which is diagonal here, to make it even simpler. The standard model should be as simple as possible. Here, in terms of the inverse covariance matrix, this I learned a few months ago is called the precision. The only person in the room who used the word precision during this week was Eugenia, who used it Monday morning in explaining what 1 over sigma squared is. And that's what this is. This is the precision of the measurement. If r goes to infinity, you have infinite precision. This is a delta function. And similarly, in the model, which I cast here in discrete time, I'll go to continuous time in a moment, the precision is called RF. It is a number that we introduced to represent errors in the model. If RF goes to infinity, the model is perfectly deterministic because the equation of motion is xn plus 1 equals f of x. These are the Navier-Stokes equations in discrete time, plus 1 over the square root of RF times the Gaussian distribution. RF goes to infinity, the errors go away, this becomes a delta function. This is the model that I call the standard model. And I'm going to show you, I want to know how to look for extrema of this function. Well, it doesn't look so hard to do, right? You just vary all the x's. However, this thing is nonlinear. In the case of fluid dynamics, it's approximately quadratic in the x's. In the case of the systems that Dan was talking about, it has power elements, it has exponential elements from the underlying circuits. In the case of the transistor, it has exponential terms. It can be quite complicated. In general, finding the minima of this function is not so hard, but we want the absolute lowest minimum because it gives the absolute biggest contribution to that integral. And finding that absolute lowest minimum in computer science-like language is NP complete, which means that you cannot devise an algorithm that solves it in polynomial time. Transfer it into the language of a physicist, it says, time to give up. Fortunately, the rest of the sentence about it being NP complete is a little comma in some of these terms, except that says, except in special cases. And we have a special case here, which I will describe to you and show you how to take advantage of it.